Hello everyone. We present an approach to optimize work surface arrangement based on the habitual behaviors. Object arrangement on a surface is essential for a variety of scenarios, while it is hard for others to do it satisfactorily except professionals. A good object arrangement takes many factors into consideration, including object attributes, human factors, object relationships and so on. However, some personal habitual behavior is different for different people, which is hard to be considered in general rule. So we intend to optimize a personalized work surface arrangement according to the personal preferences of the specific individual who will use it. Here is the framework of our approach. First, capture the human activities via the HoloLens, from which we obtain the basic information for each object in the interaction, such as category, location. Then we extract object-centered habitual behavior and human-centered habitual behavior. Through the optimization, which is made up of spatial cost and habitual behavior cost, we finally obtain an updated arrangement. How does the user interact in real? First, the user selects the objects that users daily from the real objects we provide. Then the user places the selected objects on the desk according to their own habits. Finally, the user performs some daily interaction on a desk in real while wearing HoloLens, which can record activities and provide the depth information for us. By HoloLens and detection algorithm, we obtain the projection of each object, including what and where the objects are in the 3D scene. We decompose the habitual behavior extraction into two parts, object-centered extraction and human-centered extraction. In the object-centered extraction, the weight of the object has been recorded first, and we extract the position distribution of objects from the pre-processed video. In the human-centered extraction, we calculate the range of interactions for left hand and right hand separately based on the detection of users' hands in the video, and we measure the range of interactions between individual objects. Moreover, we respectively record the index of the objects that the user's left and right hands interact with at each time during all interaction. In the optimization, we define some costs to consider the spatial constraints and habitual behavior constraints. In the habitual behavior cost, we consider some interdependencies between object and the other objects. The cost penalty ensures that the related object will be in a relatively fixed position, such as keyboard and monitor. In the interaction cost, we generate the interaction position of object by the real object T interactive distribution as this figure, and consider the movement distance and the loads carried by the user when he moves around. This cost ensures the user's use of the common interactive area. We take the user's hand interaction scope and the importance of the object into account. And we use the interactive time to evaluate the importance of objects. In the spatial cost, in a work surface, each object should be visible and safe. Some solutions may make some objects pressed, which cause difficulties for users to find them. To ensure the safety of objects, we also stipulate that objects with large weight cannot be placed on light objects. And it is reasonable to place objects with small surface on the object with large surface, while the reverse is not. Another aspect that is considered in work surface arrangement is the compactness of desktop objects. Except for necessary spaces for objects on the work surface, the more compact the objects on the work surface, the cleaner it looks and the more free space the user can use. We use the minimum coverage of all objects on the work surface to reflect the area used and calculate it from an overhead view. We search for a proper work surface arrangement by an optimization process, and simulated annealing algorithm with the simple metropolis criterion is applied to explore the solution space. This is an example of optimization process. In order to verify the effectiveness and generality of our approach, we set up several experiments. We mainly performed the user study on 3 scenes, which were created concerning the traditional shape of the desk: square, rectangle and right angle. In the qualitative experiment, we want to compare our approach with other approaches. We divided 24 participants into 3 groups, and each group was randomly assigned to a desk type. They scored for each results in convenience, harmony, and overall. From this figure, our approach is as good as the consultant approach in harmony, which shows that the effectiveness of spatial layout costs in our approach work. And our approach did not have statistically significant with user approach in convenience. It shows that our approach can understand the human behavior and learn their habitual behavior. In the second experiment, we verify the effectiveness of our optimizing approach quantitatively by the time of each approach takes and how long it takes each participant to set up the desktop to do the 3 most frequently done tasks in the different optimization results. The participants were asked to fill out 3 tasks they usually do in the order of their frequency, such as writing, reading, and so on. This figure shows the time of each participant set up the desk to do frequently completed tasks. We can find that as the user's level of frequent doing declines, the less obvious the user's habits become, and the more difficult it is for consultants to better capture the user's habits. To examine the generality of our approach, we experiment on 2 other work surfaces scenes, kitchen plane and dresser surface. For the kitchen plane, the objects we optimized are various flavor jars, cookers, and so on. For the dresser surface, the objects are skincare products, makeup tools, and so on. Here we summary our contributions. Thanks for your listening.